Now that we have begun to understand how a convolution works, and we have this thing called a kernel matrix, and then we have this image matrix, and typically our kernels are going to be 3 by 3. Not always, but that's the simplest place to start. So let's talk just about a few basic ones just to understand what these things actually do. One such option for a kernel is what we call brightness filter, and that just really changes the brightness of the image. So it either makes it brighter or makes it darker. Now we'll take a look at a script in a programming language called Python. We won't go through the exact code, we'll just see how this brightness filter works. But if you think about this, okay, if you think about this K matrix, remember these are called the kernel matrix, capital K, to keep that consistency here. And then it has these zeros for 8 out of the 9 positions, except here in the middle we have some sort of little k value. Not to be confused with the name of the matrix. It's a lowercase k. This is a capital K. Now that value of k will really, if you think about how the image processes, or how the kernel processes the image, we learned that it basically goes, it's a multiplication of the value in the Y matrix. This would be the Y matrix multiplied by the first element here, the first row, first column, or the -1 component of the kernel matrix. And then as we advance to the left on the Y image, the next multiplier from the kernel moves to the right. And so along the kernel, we kind of imagine it moves from left to right, top to bottom. And then on the image itself, we move from bottom right towards the left and then up each of the rows. So because we have zeros everywhere, except here in the middle, that means in your image, whatever pixel values you have in the first row and the outer elements of the second row and all elements of the third row, it's in the Y image, the only pixel that's going to get affected is that one right in the center. Right? That's going to get multiplied because, again, the way this works is along the kernel, we move top left to bottom right, moving in the right direction, and then the middle element always multiplies the middlemost element as well. And as a result, we're basically just going to be scaling that middle pixel. So we're only going to take into account the middle pixel of the Y image, and it's going to get factored or scaled by a factor of k. So whatever this pixel value is, let's say this is 3, if you had a little k value of, say, 1.5, well, that means that the Y new, would be all of the same pixel values that were originally there, except that new middle pixel would be 1.5 times 3, which would give us 4.5. Now, if k is bigger than 1, if we're scaling this middle component by a factor bigger than 1, then it's actually going to increase the brightness on a scale of 0 to 255. Remember, these are the pixel values that we could have. And 255 is the brightest. And what I mean by that is that will be like a bright white. And this will be the darkest. And this will be completely black. Okay, and then anything between 0 and 255 will give us varying shades of gray, essentially. It'll be a mixture of black and white. So let's go ahead and take a look at this. So here is the code. We'll, in a separate video, I'll talk a little bit about what all of this does, just so you have a sense. But what's really important here is an original image. This is just an image of some location in France. A beautiful little pathway there. And this is just showing up on a graph. That's why you have these scales. And this just tells us that this image is about, I don't know, maybe about 225 pixels by 225 pixels. So it's basically about 225 pixels squared. And that's how many pixels there are in that image. So this is the original. And then down here, we can actually specify the elements of the K matrix. Okay, so in this case, this matrix, the way this is formatted is you have the outer square brackets here, and you can see the ones that are highlighted in green. That just opens and closes the matrix. The parentheses are really just there to That's the matrix that we're feeding into and converting it into what's called an array. Okay, so in the top row, we have 0, 0, 0. So that's our top row. Then we close those brackets. That just ends the row. Comma. Now we're going to move on to the next row. So open the next row brackets, and the other green bracket there closes that second row. And we just put a k value of 0.6 there, right in the center. So that's coming back here. That's our little k value. And so ideally, this is going to scale by our image pixel values by 0.6. So we're going to end up making the image darker if this is correct. And then we have all zeros in that third row. Okay, so let's actually execute this. All right, so here is our original, one labeled original, and then this is the one that's been multiplied by this kernel with a little k value of 0.6. You can see we've made it darker. In fact, that would be analogous to saying we've made it 40% darker. We've decreased the pixel intensity by 40%. Now, if we went something along the lines of 1.6, well, now we're going to make the pixel value 60% brighter. Right? 1.6 means 100% of the original pixel values increase of 60% more. So run this, you can see we get a very, very bright image. And all we're doing there, this would be the same thing as actually taking a scalar of 1.6 and multiplying it by your entire image matrix Y. Okay, so you could also almost do this without a kernel at all. You could just scale the image by 0.6 or 1.6, but I think it drives the point home of what these kernels are really doing. Now, some of these get a little bit less intuitive. There is one called a sharpness filter, and a sharpness filter, well, as you might guess, we want to sharpen, make lines crisper. We want less of a blur effect that might be happening. And if you think about why images are blurry, well, typically that is a failure to distinguish between, let's say, the edge of, the edge of somebody's face and the background, and it kind of all just blurs together. So there's very few distinguishing features. Now, here are just some examples. There's lots of different ways to have sharpness filters. One way is to basically ignore, anytime we have zeros, we're going to be ignoring those pixel values, ignore the 4 outermost pixels. And then if you notice, we have -1, -1, -1, -1, and then a 5. So that center pixel is going to be multiplied by 5. And so it's going to basically have that, we can consider that 5 to be its weight. So we're going to weight that center pixel the most. In fact, we're typically always going to do that because that's what we're operating on, and we don't want to change that pixel value too much. But if you think about what's going on here, we have 4 weights of -1, and if you add together -1, -1, -1, -1, and 5, you get a +1. So that just ensures that we still get a higher emphasis on that middle pixel value, but we are kind of weighing into account these edge values. Another way to do that would be to have a 9 in the center and then to have -1s all the way around. And again, if you add all of these scalars together, you get +1. And in general, there are different variations of a sharpness filter, but if we let little k be some integer, then if all of these values are the negative of k, and this would be 8 times k plus 1, well, that'll ensure that our summation, again, emphasizes this middle value the most. In fact, here you can see that k is just equal to 1. If k was equal to 2, then we'd have -2s all the way around. We'd have 8 -2s, which is -16 if you sum those together. 8 times 2 plus 1 is 17, so once again, those add up. -16 plus 17 adds up to 1. Okay, let's take a look at how this sharpness filter works. Now, if you imagine, say something like this guy here, and let's say you have 1, 1, 1, 1, let's say 2, 4, 1, 1, 1, then the way this is going to work, okay, so first of all, these values are not going to get counted because they're going to get scaled by 0. And then if we think about this 1 will get scaled by -1, so we'll have 1 times -1 plus, okay, well now it'll be this 4 times this -1, so we'll have 4 times -1. Then we'll have 2 times 5. My image, we are now at -1, which is going to get multiplied by by +4. Let's see here, am I doing this correctly? Yes, and then we'll have +1 times -1, so that's this guy multiplied by this guy here, and then we'll have +1 times -1. Now, if you think about how crisp this image is, there isn't very much of a distinction on a scale of 0 to 255. There's going to be a little bit of a blur here just because those pixel values are so close together. You're going to see maybe a slight variation in the shade. But when we sum these together, let's see what we get. We get -1 minus 4 is -5. Plus 10 is +5. Minus 1 is 4. Minus 1 is 3. So we would get a value of 3, which means this +2 would become a +3. And so in a sense, what we've done is we've adjusted, if you think about it, we've adjusted the brightness of that pixel just a little bit, so it stands out just a little bit more. Okay, that's one way that we could actually think about this. We're ultimately going to try to create finer distinctions, or I should say greater distinctions among pixel values. So if we take a look at our image here, okay, this was our, let's clear, well, we'll just look at this one. There's our original, and it's not too bad, but it could use a little crispening up. So let's go ahead and just try this one here. See what that does. 0 and then -1, and here we'll have -1, here we'll have +5, here we'll have -1, and then just down here we'll have -1 as well. So that's going to be this -1. So let's go ahead and run that and see what that does to our image. Okay, now you see that there's a big difference between our original, which now actually does look relatively blurry compared to this image. Now, does it look better? Well, that's up for debate, but it definitely did sharpen the image up a bit. And maybe if we don't like that, then we can start to look at some of these other ones, which essentially do the same thing as this one, but we're also going to consider the corner values. So let's actually just change these zeros to -1s. Change these zeros to -1s and actually take into account those values, and then this one will have to become a 9. Let's see how that changes the sharpness. Okay, well you can see there's a dramatic effect. This was how we sharpened the image with that first kernel matrix with the zeros in the corner, and now it's, really we could tell all the shapes from one another much better than we could in the original image. Is it a better looking image? I don't know, maybe not, but it definitely accomplished the goal, and we'd have to fine tune and play around with this filter some more to get it to do what we want. Okay, now I won't look into as much detail on some of these other ones. We also have something called edge detection, which, as you can guess, the goal is we'd like to place particular attention on any lines that separate key features, sides of buildings, outlines of shrubs, etc. Now we can kind of do that with the sharpness filter, and you notice that it's very similar, but our weights actually will always place a 1/8 emphasis, increase emphasis on that center pixel value, because once again, if you add these together, you get a little bit more emphasis on that center pixel, but it'll only be a sum of 1/8. So let's go ahead and take a look at this one. And again, we're not saying that these are, and I think I have, yeah, let's do -1/8, and we'll just copy and paste that value, type it out each time. And then the only distinction here is that we're going to have a 1 there in the center. So this does act kind of like a sharpness filter, but you're going to see it's much more dramatic. Okay, see what I'm saying? It's much more dramatic. Probably not what we want, but it did actually, if we were to increase the size of this, you can see that where all of that white is, that's just placing more emphasis on those distinguishing features that separate the shapes. Now, of course, that doesn't look good at all. But let's go ahead and let's try this other matrix where we have -1 across the top row. We have zeros in the second row, and see what that does. In this case, notice that we're not placing any emphasis on that center pixel. And then here, I think we're just going to have positive ones. So we're really just going to consider the surrounding edges. And let's see how this changes things differently. Okay, well, I don't know that we necessarily like that, but it did place a lot of emphasis, for example, like on this little roofline ridge. You can see that that shows up as white in the picture. We can actually see the outline of the path. Does it look better? No. I mean, we can tell where all the stones are, and we can actually see where all of the, maybe we can't really see that vine very well that's climbing up the building here. But we can see outlines of all of those shapes. Okay, so that's edge detection. Typically, you're not going to want to be using edge detection to make the image look better. You're maybe looking for edge detection so that you could identify facial recognition. Maybe you could identify faces in the image. So the edge detection algorithm is typically going to be used to extract some features or identify locations of certain features. Our image wasn't necessarily a particularly good example of where edge detection is prominent, mainly because there were so many shapes that were distinguished already in that image, right? There's just a lot going on here. There's a lot of pavers, there's a lot of bricks in the building, there's just a lot of different shapes. So the edge detection is, there's a lot going on there, right? But we might be able to detect a person, the outline of a person, by using this, whereas a computer might have a really hard time identifying a person in this image. And so we could actually train a computer to do things like facial recognition by being able to distinguish people from objects. Then we have something called an embossing filter, and this is what we call a non-symmetric filter because you can see that it doesn't emphasize all the pixels in the same way. It'll make the photo kind of look like it's etched in stone, and this -0 here is actually just a 0. So we have zeros everywhere except along the diagonal, and if you remember, the diagonal is just from top left to bottom right. That's what we call the diagonal. Then we'll have 0, -1, 0, and then 0, 0, -1. So if you notice that those weights add up to 0 in this case, let's see what it does. Yeah, look at that. That's pretty cool. That's the embossing effect, and you can really see what that does. It does kind of make it look like that photo was etched in stone. So that maybe is an effect that we would like. Sometimes we want to do things to images to get some sort of cool, like charcoal type of effect, and this filter would do that. There's also, and we'll just consider one more, there are tons of other filters, but we'll stop with this one. We have the box or averaging filter, and you can see what this is going to do is it's just going to average all the pixel values together. And what this will do is it'll smooth image pixels instead of sharpening them. If you think about like older video games like Mario Brothers, where the pixels are just really kind of like choppy and distinguished, when video game developers wanted to take something that's very pixelated and kind of smooth out the pixels, they'll use something like an averaging filter. So let's go ahead and take a look at that. I'll type those in. So here I just have all the 1/9 placed, and let's see what that does. Okay, so you can see that it had basically the opposite effect of sharpening. It blurred the image a little bit. But in, again, images that you have lots of pixelation going on in, you want to often take away that sharpness, right? Because that will make the image look a little bit more organic, I guess, for lack of better words. In this case, this is a nice sharp image that doesn't have a lot of pixelation. So going from the original to the kind of smoothed or the box averaged image is not desirable because it just makes it look like, what I would see if I took out my contacts and tried to look down this street. That's about what I would see. So these are just some examples. There are lots of other filters out there. There are kernels that can be done that are larger in size, etc. Now, in the final video, we'll kind of just talk briefly about how this code works. We won't go through all the details because I understand you yourself may not be a programmer, but just so you have an idea of like mathematically what we're actually doing here, we'll do that in a short next video.